we reach the final class. And what I want to do is at the beginning talk a little bit about general results and then go through one example in slightly more details if I have time. So let me remind you the last theorem, removal of singularities theorem that I put on the board, just tiny bit formulated differently. If you have a definable complex manifold, then in it, a definable, when I say analytic, I always mean complex analytic, even if I forget to say that. Locally analytic subset where locally analytic does not need to talk about the ambient space. You just have to say that at every point there is a neighborhood at which you are analytic, and equivalent statement to that there is a definable open set in which you are analytic. But actually the definable open set is definable from X. You just put small neighborhoods around the points which are analytic. And then if you know this frontier property, which is a bit complicated to state just because of the fact that I did not put any other restrictions. If I wanted it to be, if I added that it is connected, then I would not need that at all. No, actually, no, even then I would need that. Sorry, even then I would need it. So here it is. If the frontier of X everywhere is at most the dimension of X minus 2, the real dimension, then the closure is analytic, complex analytic as well. And let me just show you as a corollary something that we discussed last time, but now I can make it more precise. If you have xt, t of t, now this can be, the t can be anywhere, a definable family of subsets of some definable analytic manifold, and even you could put this manifold also to vary in parameters. It doesn't matter, it's still everything works. Then the set you can recognize definably when this is when xt, or even you can put the closure of xt, it's the same as C analytic in M. All right, so the property of being complex analytic is definable, and it's not hard to see that the property of being real analytic in general is not definable, but complex analytic is definable. And the proof of that, well, let's define the complex regular point of xt to be the set of all x in xt such that the germ of xt at x is a complex submanifold, is a C submanifold of M. The germ of a C submanifold is the germ of a C. Yeah, is the germ of which means that it's locally R. It's enough to say that it's locally R differentiable, and that the tangent space everywhere is a C linear space. Right? So this is definable. This is definable. The family of these is definable. This is definable in T, and each reg C xt is in particular, it's even a submanifold of M, but is locally analytic subset of M. It's even a submanifold of M. All right. And now we can let's write this T0, and let's call what do I want to say? So this is one thing I will need. The other thing I will need is that xt is closed, of course, in order to be a submanifold. So now I think I can write the following. So now xt is analytic in M if and only if we apply this condition. So first of all, xt is closed. Xt closed. And let me give a name to this. I don't know, let's call it RT. And now we write for every open, of course, basic open V in M, the dimension, sorry, I need more, I think. Okay, let me write to be safe more. RT is dense in xt. Let me put it to be safe. And for every V in M open, the frontier of RT intersection V, its dimension is at most the dimension of RT minus 2. Now, the reason that this is true, well, in one direction, it just follows from here, because if RT is dense and it satisfies this property, then its closure is C analytic by this result. And if it is C analytic, the set of singular points on a C analytic set is itself complex analytic. It is known, and it satisfies that the singularity point has at least dimension 1 less than the whole of RT, so that the complex dimension 1 and hence real dimension 2 less. So one direction follows from the theorem, and the other direction just follows from the fact that the singular points on the complex analytic set satisfy this dimension property. Okay, so and this is all definable. So now we can recognize within definable family of sets which ones are complex analytic. All right, and now I'll just put the so-called definable chow. I'll just say it like that. If X, so this is another type of result like this, is definable C analytic set then X is algebraic, is an algebraic variety. Okay, so it's not, I'm not saying that it follows from that. It's another theorem which is again proven in similar way to the picture that I drew before. You find the correct, you cover it by finitely many correct proper projections, and the fact that it's sitting the whole of Cn guarantees that the projection is dense in the whole of Cn minus 1, let's say. So the procedure that I described last time now works with the projection being the whole of Cn minus 1, or a dense subset of Cn minus 1. So this allows you to actually get here polynomial functions. And because we know that polynomial functions, global polynomial functions are algebraic, then the set becomes an algebraic set.
So here, this is not really an analog directly of the original Chow theorem, because there you assume that you have a compact.
Right. So this is a strengthening. Yeah, this is a, so in particular we prove in general, but this is of course Chow theorem. We prove this result as well in the general setting of K and R. And then you can say that the Chow's theorem, the classical Chow's theorem, follows from that, because in P and C, every analytic set, if you remember, is definable in the omnium structure R sub n. Right. So in particular, you get Chow's theorem this result.
One question here, just to make sure, when you say definable C analytic set, you mean definably C analytic?
Yes.
In the strong sense.
Yes, but as I said, yeah, this is fine. But as I said, this is all. Now, you know, by this argument, these are all local properties. So definable analytic and definably analytic, it's all the same. They are the same.
Oh, yeah, because of wait a minute. Why is they are the same for R sub n, but
for C, no, they are the same for C to the n. As I said, one of the things we prove using that is whenever you have a definable analytic set, you can actually recover the functions which define it explicitly with finitely many, after you cover X by finitely many sets. So actually you realize it explicitly as given by finitely many open sets with finitely many families of functions.
Yeah, but these functions should also be definable.
Yes, I'm saying that, yeah. You remember we wrote yesterday the expression for them. They just are obtained by this W minus phi IV, and you just take the closure of that.
It's all the same. Good.
Yes. So as a corollary, we get again this uniform definability if xt, t and t is a definable family of subsets of C to the n, then the places where these are algebraic is definable. Then the set of T and T such that xt algebraic is definable. Okay, and here I can put an exercise for the for students, for anyone. Show that this fails in O minimal structure. So show that the analogous result for real algebraic analogous result fails for real algebraic xt in R to the n, namely if you have in an O minimal structure a definable family of sets, you cannot recognize definably those which are real algebraic in Rn.
Even if you work in the smallest O minimal.
I don't know. So I would guess that there.
Algebraic structure.
I would guess that there maybe it is true.
Yeah, I believe that there it is actually the case.
Right. And maybe true in polynomially bounded structure for similar reasons. Sergey says no from the back, so I don't know. Sorry? But these are not local. This is not local statement. This is global statement. We're not asking whether locally it is real algebraic. This we cannot tell. Well, this we cannot tell, I think, even here. I'm not sure we can. Although. But this is not definable in the real field. You say maybe it's not true in the polynomially bounded setting. Yeah, maybe this is true. Yeah, maybe not. All right. Let me just say a word. I'm not sure what Jacob exactly how he's going to do. I mean, I'm talking about the little that I know of the Gaga paper and the Hodge structure, but just an idea of how this this type of Charles theorem can be used. I'm not sure if he will do it this way, and I'm totally oversimplifying, I'm sure, the general picture, but this is the picture that I got off when I was able to understand pieces of their paper. So you have X an algebraic variety. And they work in more general setting of an algebraic space with sheaves, etc. But let me just do it in a very elementary kind of description. And then you have Y, just totally analytic, nothing we know about it, analytic space, so analytic, let's call it analytic space, but not assumed to be definable and not definable. Now, in practice, what will happen, I will just say buzzwords that I'm not sure I understand fully, or actually I don't understand fully. Then Y will be, I think, what's called the period domain related to what's called a variation of Hodge structures. X will be supporting so-called variation of Hodge structure on it. So a family of Hodge structures parameterized by X. And then there is a natural map, apparently, F from X to Y. Again, Y is not definable. I think this is usually how they write it. It's some period domain modular lattice, but this is not definable. And this is analytic. Okay, but the range is not definable. And now, a lot of work is put into showing that although the range is not definable, the function is definable to a piece of the range. So maybe into a fundamental set in the range now. Show that F from X into some subset of Y is definable, I think, in Rnx. They always work in Rnx.
But then you restrict F to the inverse image of Y1, I suppose.
No, but F is the whole, it's still X.
Oh.
It's still X. So Y1.
Oh, F maps X all into this subset Y1.
Right,
oh.
right. I think the whole X. Maybe they remove some small pieces of X, but I think the whole X.
Oh.
Still, they can identify the place where it lands. It's not a surjective map by any means. This is somehow the range is exactly like the, I think for every point you correspond like a modular point in the moduli of variation of Hodge structure, I think, which corresponds exactly to the fiber above X in this variation of Hodge structure. So depending on the variation of Hodge structure above the point, you land in the point in Y1, which classifies this variation of Hodge.
The equivalent relation of X saying that Fx is Fy is definable in
exactly. So now the relation exactly that x1, x2 in x squared such that f of x1 is equal to x2 is definable. And because it's given as a kernel of an analytic map, it is an analytic subset of x squared. So now we have on an algebraic variety, an analytic subset, so x squared is also an analytic variety. So now this relation by Chow's theorem, by this definable Chow, E is algebraic. And now we use the theorem from the theory of algebraically closed fields. If you want, in model theory, we use elimination of imaginaries in algebraically closed field. So now X mod E, which is the image, right? In something, it is in bijection with the image, is a constructible set because of results in algebraic geometry that says that when you take an algebraic relation, you mod out a set by an algebraic relation, the quotient is constructible. It's not definable. It's a Boolean combination. Is constructible. All right, and in my naive way of understanding, a lot of the work, this is all related to so-called Griffith's conjecture. And most of the work that goes into the, well, first of all, I simplified because they don't have an algebraic variety, they have an algebraic space, and this is not exactly Anyway, it's all in a different language, but if further understand, a lot of the work comes to replacing this by actually an algebraic object. And this is not model theory anymore. This has nothing to do with O minimality. And a lot of hardcore mathematics goes into proving that this is in fact algebraic. And this is the theorem of Griffith, the conjecture of Griffith that they proved says that a certain image, the image under blah, 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 variation of Hodge structure, the image in the period domain is in fact algebraic. And if I understand correctly, a lot of work goes into moving from here to here, although in the paper they never mentioned this fact.
But constructible is very close to algebraic.
Right, but I think this is for model theories, but I'm not sure if.
I thought that there's even a general theorem that the constructible sets can be made in a natural way into a variety, but maybe I misremembered that.
But I think I'm oversimplifying because maybe this is not a constructible set inside Cn. It's some sort of a constructible space. I don't know. I'm being very vague. So, but when you, hopefully when we hear the talks of Zimmerman, we can recognize at some point this step. Or even if you look at the introduction to the Gaga paper.
But for example, there is also the general fact that the constructible group is isomorphic to an algebraic group.
Right.
By this.
Yeah, but as we know, the group plays an amazing, very important role in this. You have to move things around, and
if there is a group acting, for example, you might still be able to. I don't know if that's the case here.
I don't think it is. I don't think there is any group acting, but maybe I'm wrong. All right, so this was just. And now the time that I have left, maybe in the last half an hour, I want to go through one example which has just a little bit of this flavor, and to see how in a very elementary case one can prove definability. Okay, so now I will not talk about removal of singularities or Charles theorem. I will just try to produce in some very, very baby case, I will try to go to this step. Nothing to do with this setting, but where is it? Just to show that a certain function, a transcendental function, is definable when you restrict it to a proper domain. Okay, so the setting is so-called the modular space of elliptic curves. And so I remind you, we talked last time, but assume that we have is a lattice in R2, in C, sorry, in C, which means that R independent. And we saw that C, let me call tau bar, the pair, C mod lambda tau bar. I'll write it as, for now, F T bar, can be given the structure of a complex manifold without any, just in the semi-linear language, can be endowed with definable C manifold structure. Actually, I'm not sure I need this even. Yeah, this is not necessary here. Just using the two charts, basically. No, three charts maybe you need here, all semi-linear charts. But in the case of, and this is also a compact complex group. And we know from the standard theory, from the classical theory, that to F tau is isomorphic as a complex analytic object to what I'll write E tau in projective space. I think you can always bring them to 3, but and this is an elliptic curve. And when we say isomorphic, I mean it's isomorphic as a complex analytic group. So it's isomorphic. The group goes to an algebraic group, the complex structure goes to the complex structure here, which has a natural complex structure. And these are all two-dimensional real tori, right? Okay. Now, just as a comment, when you go from C1 to Cn, you can perform the same thing with a lattice. Again, on the left side, you will always get a definable complex torus. But as we know, when you go from dimension bigger than 1, this embedding exists only for very specific lattices which satisfy certain condition, and then the image is an abelian variety. All right, but we will just do it in dimension 1, where you can always do the embedding. And now I'm interested a little bit about what happens on the left side. So some facts. We have E tau. And now the last thing I want to say is that you can always do some manipulation, and we may assume always that tau has the form of tau 1. So one of the base elements can be chosen 1, where tau is in the upper, I'll write it H, the upper half plane, or the Z, such that we may assume, because every elliptic curve has another elliptic curve which is isomorphic to of this form. All right. So now we can write E tau without the bar, because we just care about the second, about the right, in terms of the picture. If this is the upper half plane, we have 1 as one generator of the lattice, and we have tau, which is the other generator of the lattice, and the fundamental domain is here. Okay, and the theorem, the classical results tell us that we have a condition to when two elliptic curves are isomorphic, and this is if and only if there is G in SL2Z such that G tau 1 equal to tau 2, and now I have to say how square matrices act on the upper half plane. And by this, I mean that if G is A, B, C, D times an element tau is A tau plus B divided by C tau plus D. And you do a computation actually for any G in SL2R. For any G in SL2R, this takes an element in the upper half plane and gives you back an element in the upper half plane in H. Okay, this. But not only that SL2Z acts on the upper half plane, it exactly tells you when two elliptic curves are isomorphic. Okay. The next analytic ingredient we need is that there is actually a function So this is fact 1. Fact 2, there is a holomorphic transcendental function J from the upper half plane actually onto C, such that J of tau 1 equal to J of tau 2 if and only if SL to Z of tau 1 equal to SL to Z of tau 2, which means they are in the same orbit of SL to Z. Right, and this is if and only if E tau 1 is isomorphic to E tau 2. Okay, so J kills the orbit equivalence relation on H, and that's why you may think. So you may think of C as having a representative for every elliptic curve up to isomorphism. That's why C can be viewed as the moduli space of elliptic curves.
Now, when you say that eta 1 is isomorphic to eta 2, this means as algebraic varieties over the complex.
So let's think, it can mean many things, right? It can mean as real objects, but as real objects, they're all isomorphic because they are all S1 cross S1 with a group on them. So we must mean something with complex. And now it turns out that actually, if they are just isomorphic, yeah, as complex, even as, well, let's think. If they're isomorphic as analytic objects, because they live in projective space, so the isomorphism will also be an analytic subset of projective space, then it will be algebraic automatically by Charles' theorem.
Right.
So to say that they're isomorphic, you can say either as algebraic object with an algebraic, but actually, equivalently, you can just say that they're analytically.
Okay.
All right. So now notice that it means that the pre-image of a point in C is a discrete infinite set because it's the orbit of SL2Z. Right? So every pre-image of a point in C is a discrete infinite set. So immediately we see that J cannot be definable in an O-minimal structure, right? So J inverse of A is infinite, discrete, so not definable. So J actually, we can say, is not definable in any O-minimal structure. So let's get this out of the way. And this is, as we said last time, this is typical to the applications, that you have some transcendental map. This is called sometimes the uniformization of C from H to C, but all these maps usually, because they have like a universal cover feature to them, they will never be definable because the pre-image of a point will be infinite discrete. And a lot of what is going on in trying to apply O-minimality is to find the proper domain on which it is definable, but still captures the whole range. So this is what's called a fundamental set. So let's talk about fundamental sets for the J invariant.
What is the image of the map J?
Sorry?
Do you know the image of the map J? Or
it's surjective. It's surjective. Sorry. Yeah, I put this double arrow.
Oh, yeah.
The image is everything. Is everything. It covers C. Every element in C is associated by this to an elliptic curve. Right? And those of you who know under Oort, there were issues there about trying to tell, well, in C is not, you usually take the Cartesian product. You associate to every point in C the elliptic curve, and then you can ask whether it has complex multiplication or not. And this specializes. This gives a collection of special points in C, those whose pre-image has certain properties. So you look at the elliptic curve, and you ask, does it have this property or this property? And you obtain in this way an infinite subset of C with various properties. All right. J. So I'll draw a picture that I'm sure many of you have seen. I hope I can do it in almost every book. It's a favorite book of a favorite picture of graphic designers when they look for a picture related to mathematics, because then you put the other ones as well and it becomes very nice. But the fundamental domain, I'll try to do it. I hope I'm precise. You go here to, no, this is not minus half. This is at the unit disk. So this is minus 1, 1. And now you go here to minus 1/2 and 1/2, I think. And maybe let's do it here with straight line and here with open. And let me write it, I hope, correctly. So the F is all the z such that absolute value of z, first of all, is greater or equal to 1 on real z greater or equal to minus 1/2 less than 0. This is the left side union all the z, absolute value of z greater than 1 on the rest. So this is when the real part of z is greater or equal to 0. I hope I got the 0 right, and less than 1/2. I think this is it. Maybe I made a mistake. All right, so here you take the unit circle as well, but on the other side you don't take the unit circle. I think this is right. All right, and the statement is that this is a fundamental set for J, which means that every orbit of SL2Z has exactly one representative here, correct? Every SL2Z orbit has one representative in F. So it means that the restriction of J to F is surjective as well, right? So it means that the restriction of F to G, of J to F is surjective. So we will capture the whole behavior in the range. We will capture all the elliptic curves just by looking at J restricted to the fundamental set.
Has exactly one representative.
Sorry?
They said it one axis, but exactly one.
Yeah, exactly. Yeah. Actually, yeah, one, it's fine. I don't need it. I don't mind to take the, for what I'm going to do, I don't mind if you have a little bit more. I just don't want more than, I want finitely many with a fixed number. This is important. Okay, so as I said, hence J restricted to F from F to C is still surjective. So if you want to apply more minimal techniques to the problem, let's say, of special points like under-ordered problems, then you might be enough just to look at J restricted to F. And then, for example, you can apply techniques like Pila-Wilke techniques and everything to try to count points, etc., etc. All right, and this is, so let me prove, I hope I can do it in time, that the function J restricted to F is definable in Rn X. All right. Consider, let me call it, yeah, just so I don't have to carry all the time, let's call it x z e to the 2 pi I z. So it's a variant of x, right? Times the. So as we said, of course, this is not from C to C. This is not a definable function by any means in an O-minimal structure. But now I want to look at X restricted to F. And the first observation is definable in R. You don't need any, it's enough to put sine and cosine, restricted sine and cosine, for the same reason that X was definable on a strip, right? We just multiplied by I. So we just shifted it, and now we move to this one. So actually, this X is definable on the whole strip. If the original X was definable with bounded imaginary set, bounded imaginary value, then this one, because we shifted by 90 degrees, is definable on any strip with bounded real value. Okay. And now let's see what it does to f. And actually, I don't care about this precise f. I can cut it anywhere and I'll be fine. Let me first comment that on every bounded part, J is definable because it's an analytic function. So in R sub n, yeah, I should have said that on every bounded part of this, J is definable because it's a box, more or less. You can even extend it to the box. And we know that real analytic functions on boxes are definable in R sub n. So maybe I should say, just as a comment, notice that J is definable just in R sub n on F intersection any im z less than, well, I don't need even absolute value. Right? Because the real and imaginary parts will be defined, will be real analytic, and it's a box, so everything is fine. So the problem is really what happens at infinity. And this is why we apply this x. So what does x does to infinity, right? So we have this picture. We apply this e to the 2 pi I z. And now let's see what it does. So we have e to the 2 pi I x plus iy. And we get e to the 2 pi I x times e to the minus 2 pi y. Right? So what is it? This is well, if we go with x long enough, we will just cover a circle. And the radius of the circle, right? If x goes between -1 to 1, well, even if x goes from -half to half, this covers an angle of 2 pi of, sorry, from -1 to 1, it covers, no, from -half to half, it covers an angle of 2 pi. And this is the radius where the maximum of the radius is obtained. Let's say if this is A, obtained here. So what I want to say that the image of this is a disk, but without zero. Puncture disk. Okay, with the boundary being exactly the image of this. So we might as well add both of them. I don't care to prove that J is definable on more than that. So this is a puncture disk. All right. Now, notice then that SL2Z is generated, well, by two functions, 1 over z and z plus 1. But in particular, z plus 1 is an element of SL2Z. So z plus 1, this map, it corresponds to 1, 1, 0, 1 in SL2Z. So what do we mean? It implies that J of z plus 1 or tau plus 1 equal to J of z. So J is invariant under action by z goes to z plus 1. Okay. And we have x of 2 pi I z plus 1 equals to x of 2 pi I z times x of 2 pi I times 1. So we also have that x behaves like that. So what is the bottom line of that? Is that if we have this picture of f here, d star here, x here, and here we have the j that we're after, then actually j factors through a point, through a map from d star into cy, because you want to know what each point does. You take a point, you take its pre-image, it will be invariant under z plus 1. It doesn't matter which one you take. J is well defined on it. So now you can put some map here, J tilde, thus J factors to function J tilde from D star into C, which is analytic just by the picture function, analytic function.
You're going too low for us to see it.
Sorry. All right, so what I want to say is that J, actually even here without restriction to F, equals to first doing X. Well, sorry, restricted to F, and then doing J tilde. So if we knew that J tilde itself was definable in R and X, then we would be done, because Gen J is the composition of this restricted to F, which is definable, and J tilde. And now we have a function on a puncture disk, which is analytic. So the only problem is, does it have essential singularity or not? If it doesn't have an essential singularity, then it's the quotient of two analytic functions. If it does, we are in trouble. So here comes again, the standard theory of analytic, I guess, analytic number theory. So fact, the image, as you approach within F to infinity, the image, the limit, sorry, of J of Z in absolute value as Z goes to infinity in F exists and is plus infinity. So you don't have essential singularity along this strip at infinity, and as a result, right, when we approach infinity on the strip, we're approaching 0 on the disk. So as a result, the limit of J tilde of that as Z goes to 0 now anywhere in the disk exists and is plus infinity. Right? So now it means, remember, an analytic function, this means that the singularity is not bad, it's just a pole. 0 is the pole of J tilde. Hence, there are analytic, let me write it first in the analytic language, analytic Fg in a neighborhood of 0. Actually, one of them can be just the power of z, but it's okay, we can write it like this, such that J tilde is equal to Fz over Gz with z different than 0. But F and G are definable in R sub n, so J tilde is definable in R sub n. Fg, analytic in a neighborhood, there are germs of analytic function in R sub n, which implies J tilde defined in R sub n, which implies that the composition is definable in Rn exp. That J restricted to F is definable in Rnx. And in fact, it turns out, as we proved in the original paper, that when we wrote this, I mean, we proved something much stronger about uniform definability of Weierstrass P functions, and this came out of that. But it's not hard to see that its exponential is essential. Why? Because once you add J, it is not polynomially bounded, and then by Chris's result, the exponential function is definable. So having J there forces you to have X, the real X.
By the way, this J function, it's usually, I think it's usually written as just a small j.
I think the algebraic one is written with small j. There is the image of this map on the modular space is written with small j, and then it associates to every elliptic curve actually an algebraic function. And this is usually, I think, denoted by little j. And this is the analytic function. I think it's usually denoted by capital J, but maybe I'm wrong. All right, we finished. So I just want to point out what happened here along the course, which I think is really nice. If you remember, sometime 4 weeks ago, we started with a model theoretic problem. Actually, the problem that interested us was Hilbert's trichotomy in the setting of O-minimal structures. We were led somehow trying to solve it to questions about arbitrary complex analysis, like in an arbitrary O-minimal structure, in order to solve this model theoretic problem, right? Not totally abstract problems, Hilbert's conjecture from the late 80s, from the late 70s. And then we were carried out and we started proving more and more results about this abstract setting, complex analysis in abstract setting. And at the end, actually, we did not ourselves, people who were interested in things like that, I think Jacob started with that, notice all this work and say, oh, this could be very useful to solve other problems. So, and then it turned out now in Hodge theory. So I think it's very nice and interesting how these ideas can start from questions in abstract mathematics and flow into eventually very concrete, hardcore mathematics. That's it. I understand I have a question session. I will try to be there from Israel on Tuesday. I'm leaving on Sunday. If anyone wants to ask questions, I have time for questions if you want. There is a seminar now, or?